No? Okay, so I wanted to share this presentation with everybody. Excuse the parakeet in the background. That's Lady. My kids decided that she has to be in my office. So anyway, hopefully she'll restore my NAD and not lower it some more. So I'm a dietitian. I'm not a doctor. This isn't medical advice. This is only to provide information, not to diagnose or treat a condition. Consult with your personal health care provider prior to making any changes to your diet, supplements, medications, or lifestyle. So now that we got that out of the way, we can move on to the next thing. So I want to talk about this pivotal point in metabolism. It's the enzyme lactate dehydrogenase that runs this reaction that converts pyruvate and lactate back and forth. And so I think it actually becomes a pivotal point in metabolism when we have mitochondrial disease or impaired TCA cycle, which is actually within the mitochondria. So it's also considered mitochondrial disease. And so you can see here that there's NAD. I got rid of the parakeet. Don't worry, she's still alive. She's just in the other room. So when we run the reaction from pyruvate to lactate, and pyruvate actually comes from glucose metabolism. So when we run from pyruvate to lactate, we actually generate NAD. But when we go from lactate to pyruvate, we generate NADH. And so oxalate actually causes problems by inhibiting lactate dehydrogenase. And I think it's in a dose-dependent manner. And of course, there's varying abilities of our bodies to absorb oxalate because there's bacteria in our gut that can metabolize oxalate. If we have a bad gut microbiome or leaky guts, then we'll absorb more oxalate. And so, of course, this is also a factor as gut health. It always is. It seems like it's never ending. And so here we are at this point in metabolism with lactate dehydrogenase. So if this enzyme is inhibited, the recycling of NAD and NADH in the cytosol outside of the mitochondria comes to a halt. This shouldn't be a problem if we're making adequate amounts of NAD within our mitochondria. So we're recycling it well. So here's an entire look of what's going on. You can see that glucose is happening. This is a cell mitochondrial membrane. It's happening outside in the cytosol, glucose to pyruvate. And here's the reaction from the previous slide, pyruvate to lactate. And so we're kind of just going back and forth between these. Lactate is typically made during anaerobic glycolysis. And, we think, oh, well, that only happens when we exercise, but actually it happens quite often. So, we don't always have enough oxygen in every single cell. There's always a fluctuation between carbon dioxide and oxygen. And some people, especially people on, valproic acid and some of the other seizure medicines, like zonisamide, and many other medications, they're carbonic anhydrase inhibitors. And so this can alter our ability to exchange CO2 and oxygen. I know that valproic acid also inhibits cytochrome B5, which helps you to hold on to oxygen in the blood. So again, at any given moment, we may be making lactate, which should restore NAD levels. It's just a cycle. We go between these. As soon as you eat some oxalate, though, bam, you shut off LDH and you can't make lactate anymore. And that also means in the cytosol, you're not recycling NAD. Okay, so NAD, why is it so important? Because NAD as a whole fuels our ability to make energy from our foods. So down here, glucose goes through pyruvate down to acetylcholine, and then it enters this thing called the TCA cycle or the tricarboxylic acid cycle, also called the Krebs cycle. And so it goes through this cycle and it gives off NADH, and also FADH2, and these are sent to the membrane of the mitochondria, and then the NADH and the FADH2 are recycled back to NAD and FAD, and so this helps to make an electron gradient. So we're like kind of pushing electrons along this gradient, and the hydrogens from the NADH and the FADH2 are pushed to the other side of the membrane. And then that eventually results in the making of energy, ATP, the stuff that we use, like what I'm using right now to talk. And it's a good day because it's been 3 days since I had tons of chocolate covered cashews and I had plummeted into like massive brain fog. So I'm using lots of ATP right now. So how do we break this? How do we get broken in this mitochondrial space right here? I'm only going to go over a couple things because I have some stuff in the background that I'm working on. I actually think that we can get damage to our mitochondrial membrane where this respiratory chain happens, where we make our ATP. It can be broken by vitamin A in excess. So vitamin A toxicity can break this chain, and that's something I'm working on researching in the background. Also, inadequate choline intake can cause damage to our mitochondrial inner membrane because we need phosphatidylcholine or other sources of choline to make a thing called cardiolipin. And what cardiolipin does is it's kind of like this component of the membrane that helps all of these complexes, complex 1, 2, 3, 4, and 5, stay in the membrane. So we can get impairment right here. And if we have an impaired mitochondrial respiratory chain in the membrane, then you can see that we won't be regenerating NAD. And we'll be reliant, this is my theory, that we're reliant on this pivotal lactate dehydrogenase reaction. Okay, so let's go to here. So what do we know now in our environment that definitely impairs the at least one of the enzymes of the mitochondrial membrane, and that is the drug metformin. It impairs respiratory complex 1. The reason why people take metformin is because they want to lower blood sugar. So what happens with metformin is you block respiratory complex 1, which is sufficient enough to lower ATP levels. And when ATP levels get low, it sends a message up to the cell to increase glycolysis, because when you take glucose and you turn it into pyruvate, it's not shown here, but you generate a little bit of ATP. So when you block your body's ability to make ATP, it makes you have to use up glucose faster, and then your blood sugar goes low. Brilliant, right? Wrong, because now we have this problem down here. Well, we are not recycling NADH. Okay, so that's one way. I'm not a fan of metformin. Metformin can also cause a thiamine deficiency, which can contribute to this horrible cascade as well. You actually have to have thiamine to go from pyruvate to acetyl-CoA. So you're just not going to make energy well. There's other reactions, of course, that require thiamine, but this video would be forever long if I kept going on. Okay, so actually, I could say that this one down here in the this alpha ketoglutarate requires alpha ketoglutarate dehydrogenase requires thiamine as well. So you really impair the TCA cycle and the mitochondrial function when you take metformin. Okay, so the next thing I want to talk about that can screw us up is melatonin. High dose melatonin, I'd say anything like, it depends on the person, because this whole thing is like an additive effect. But I would say anything over 10 milligrams in a day would be considered high dose melatonin. So melatonin actually helps the body to, it's an antioxidant, but it's a strong antioxidant. So it ends up making NAD become NADH. So you put the mitochondria in a high NADH state. And then when NADH is high and NAD is low, then we're going to end up having low energy levels because we won't make as much ATP. And then on top of that, we're going to end up making fat. And I'll explain that in the next, what I'm talking about now, iron. So if you have iron deficiency, iron is actually required for, it's required for this enzyme conatase, but I also believe that it's required in complex 2, which is right here, which is succinate dehydrogenase. So If you have an iron deficiency, though, the biggest pivotal moment that this is causing a problem is right here at this enzyme aconitase. So if you can't go from citrate to isocitrate because your aconitase enzyme is sluggish, then you're going to have a buildup of citrate. And I have an arrow going out here to fat, but what actually happens is this citrate leaves the mitochondria and it goes out into the cytosol and it is built into fat and you become fatter. So iron deficiency is actually a metabolic curse and it leads to obesity. And the majority of people that I see that are obese are definitely iron deficient. And it's a vicious cycle because the more obese you get, the more a hormone called hepcidin increases, and that impairs your absorption of iron. So if you are obese, please go to your doctor and have your iron levels checked. And then also ask them if they can give you IV iron, and then work on factors that help to lower hepcidin levels, which is kind of tough because one of them is weight loss. And then another one is as having normal vitamin A metabolism because you require a small amount of retinoic acid to be able to downregulate hepcidin. Okay, so when iron slows this down, basically, I said you were going to start to make fat, and it is 100% true, you will. But if your NAD levels are low, then this whole cycle can't run. As you can see, there's NAD required here at the point from malate to oxaloacetate. You need NAD down here for alpha ketoglutarate, dehydrogenase, and you need NAD over here as well. So as we become lower and lower in our NAD levels, then and we're not able to recycle them here at the respiratory chain, especially at complex 1, then what happens is we become reliant on cytosol NAD recycling, and that's the reaction between pyruvate and lactate. Here's the crazy thing is that oxalate potently inhibits lactate dehydrogenase. Potently. I like that word. And so it will lead to very low cellular levels of NAD. And basically, you will come to a screeching halt. And that was what happened to me this weekend. I have been on a low oxalate diet, about 50 milligrams a day. But just our whole family is involved in this because our youngest daughter, Zoe, has very high sensitivity to oxalate. And it will put her in the emergency room vomiting if she has more than 50 milligrams in a day. So I had about 156 milligrams in the form of chocolate-covered cashews, and it was a downward spiral. Within about 3 or 4 hours, I started to feel very brain fog-like. I started to be very lethargic. My gut started to slow down. I started to have acid reflux. Yeah, it could have been the chocolate, but it lasted for days. So it wasn't the chocolate. And then I was just exhausted and I gained 4 pounds, and I don't usually gain weight that fast. So it's quite interesting. So I guess comment and let me know what you think of this. And there's a few other factors that we could talk about eventually that alter NAD levels too, but these are the big ones I was thinking of. Thanks for listening.